This video will explain problem number 24 of chapter 4. This problem has two completely different parts to it. So we'll start with the free body diagram for part A. So part A, they actually start by looking at a diagram from the top view, I believe they say. So you have an object here. There's a force going down. Force going down is 16. So we call it force 2. They say it's 16.0 newtons. And then you have a force to the left that was 10 newtons, so it shouldn't be as long as force 2. We call that one force 1. That was 10.2 newtons. Now, you want to make sure you're labeling which way you want to be positive, so I'm going to say going to the right is positive and going up is positive. And the mass of this object is 27.0 kilograms. So with the signs in mind, the force of 2 is negative and the force 1 is also negative. They're asking for us to figure out the sum of the forces and the acceleration. I'm going to go ahead and write that. Last time I did this video I actually forgot the acceleration, so I'm going to say sigma F and A needs to be found. So, to make sure you guys understand how to find these forces, or the sum of the forces, you have to look at it two different ways, okay? Or you don't have to look at it two different ways, you have two options, but you have to look at it one of two ways. We could do the, I think they call it the parallel method, might be called something else method, so I'm pretty sure it's the parallel method. Basically, you start at the head of 1, so the arrow is the head, and you go from the head and you go parallel to the other force. So if I start at the head of F1, I need to draw a dotted line parallel to F2, and then you would go to the head of F2 and draw a line parallel to F1, like that. Where these two intersect, that's where the resultant should be. Now you can do this actually with more than one force if you have them head to tail. Okay. Now, starting from the object, we do a dotted line like this, and then that would be the resultant. So this arrow I'm drawing right there, that'd be the resultant. Now you don't draw it solid all the way through because it's not actually a force that's there. It's just the sum of the forces we're looking for. That's the parallel method of doing it. A lot of people like doing it that way. I'm not one of them. I actually like doing the head to tail method, which is very similar, but actually I'm just going to draw the object again. So if this was the diagram we had, what you do is you actually pretend you're moving the arrow over to the left side. So in the computer, you should be able to do this pretty easily. We'll see. I want to cut this arrow and move it. Oh, doesn't look like that's, oops. Yeah, it looks like that won't work the way I thought it would. Alright, that's okay. I can just, can I delete that? Should be able to delete it, there we go. Well, fine, let's just do it this way. The manual way that you do it on a pencil anyway. So basically you're saying you want to draw another force, do it in red. So you draw the tail to the head. So this red arrow is actually a duplicate of this arrow that I moved over there. Now, when you do it this way, basically this is gone, and you can draw the resultant from here. So going from the tail of one to the head of the last one. The reason why I like this method more is it works if you're connecting multiple vectors very easily. So you literally just keep plugging vectors from head to tail over and over again until you get your final. Okay, so that's the reason I like that method. But a lot of people like using the parallel method that I showed you above. Doesn't matter, just as long as you know how to do one or the other. Okay. Now, to move forward on this problem, we can label. I'm going to label this one, and then I'll label this one too, just to be fair. So we're looking for that force. It's really easy to do that when we have the two legs. It's just Pythagorean theorem. So sum of the forces is going to equal the square root of F1 squared plus F2 squared. So the sum of the forces will equal the square root of negative 10.2 newtons squared plus a negative 16, and I messed that up, 16.0 newtons squared. Okay. I accidentally made that full screen. So negative 16.0 newtons squared. I'm not sure exactly why, but I've heard that some students are having an issue with squaring the negative number and getting a negative answer. I am not sure if that's a calculator setting. I've never had that happen to me on my personal calculator, so I don't know if it's a setting that somebody might have changed on accident or didn't change back to something. But if you know your calculator is doing that, or if you didn't realize your calculator is doing that, double check. But just don't plug the negative value in when you're squaring it if you know you're not supposed to get a negative value. Okay, in this case, we know negative 10.2 squared is going to be a positive number, and negative 16 squared should give us a positive number. So don't bother putting in a negative, just go ahead and plug in what you get. Now you should get an answer of 18.9 newtons. With significant figures, you'll have 19 newtons. Okay? And we're going to be using a positive because we're going to be answering polar. So you always want to use positive when you're answering polar because it's just showing that it's going the direction that your angle specifies. Because I'm going to be answering polar, I'm also going to want to make sure I put a clear system here. So right next to the diagram and the coordinate system, I'm going to say that I'm going to have a north, south, east, and west, like that. Which makes sense because we're doing a top-down view. Now we know the sum of the forces. We could go ahead and find the angle right now. That would make sense. You could also find the acceleration, doesn't really matter, but let's go ahead and find the angle. So tangent of theta, and I'm going to say theta is this one right here, because it's on both diagrams. I'm going to say tangent of theta equals F2 divided by F1. So that means theta will equal the inverse tangent of F2 divided by F1. this 18.9 newtons I listed, it should have said 18.97 newtons. Sorry about that. We're doing 3 sig figs, so it's actually going to be 19.0 newtons. Okay, so now this angle, we say 19 degrees at 57.5 degrees. Now we have to give our cardinal position. In this case, it's south of west. And I'm going to just highlight this answer. You guys obviously would box it, but I'm going to be highlighting it just because I think boxing this would make it messier. This is so thin. That's better. Okay, so that's just my sigma f. Now we have to find the acceleration, which really isn't that big of a deal. We just have a equals sigma f over m, and we can go ahead and plug in the values for the sum of the forces and the mass, considering it's already isolated. So we go ahead and say 18.97 newtons. So we want to use the actual number, not the rounded number, to find the acceleration. Divided by 27.0 kilograms. And you'll have an acceleration of a positive 0.7027 meters per second squared. So we need to have that answer with significant figures. So we'll go ahead and write A equals a positive 0.703 meters per second squared. Now this part should make sense. If the force causes the acceleration, then whatever angle the force is at, the acceleration also needs to be at. So we don't actually need to recalculate the x and y components of the acceleration. We can just go ahead and keep the same angle, 57.5 degrees south of west. And so this is your answer to part, or not part B, the second part of part A. Part B is a completely different diagram. So that's the answer to A. Okay. Now part B, we're going to have to pretty much start over from scratch. So I'm just going to scroll down. Some of the things we did in A will be used, but most of it is different because of the fact that the forces are not all lined up along the axes. Some of them are at, or one of them's at an angle. So we have a free body diagram. We have F2 equals 16.0 newtons. And then this time F1 is at an angle somewhat like this, I think. Shouldn't have been that long. There you go. So you have F1 equals 10.2 newtons. They tell you this angle here is 120 degrees, which obviously means you draw your dotted line for the horizontal, that this part down here, theta, will equal 30 degrees. So it's 30 degrees south of west. Okay, and put in the signs. Oh yes, so F2 would be positive. F1's going to have components that are negative and positive, so we're going to wait on labeling F1. And then the mass is still 27.0 kilograms. Let's see, we have to break this down. Before we even bother drawing these reason, I think it might be useful to label all the forces you know in a list. So you can say F1x is going to equal positive 10.2 newtons times the cosine of 30 degrees. Now the reason why I'm recommending that you do it this way is it allows you to account for the signs and to make sure you don't mix up the trig functions. Okay, it's pretty much the only place you can go wrong here. So when we do F in the y direction, now F1 and goes in the negative y direction, so it's going to be negative 10.2 newtons, and then you're going to have the sine of 30 degrees. F2y, or F2 in the y direction, is the full vector because there is no x component. But I'm still going to go ahead and write F2x equals 0 newtons, just to be sure that there's no mistakes made. And we're looking for the sum of the forces and the acceleration. So I'm going to box those. Now that we have a nice complete list, let's go ahead and plug in the values. I'm going to do some of the forces of x first. I'm going to end up needing more room later anyway, so I'm going to zoom out now. And then I can just write them to the right. So the sum of the forces in the x equals, and we know F2x is just 0, so we can actually just cross it off there and just write a positive 10.2 newtons times the cosine of 30 degrees. So the sum of the forces in the x direction equals positive 8.83 newtons. Now we don't box that because that's not the actual answer we're looking for, that's just a step to it. It's also why we don't round it. Now we need to look at the sum of the forces in the y direction. So the sum of the forces in the y direction will equal, let's see where we can put, I think I'm going to go ahead and put the second one first, just so it's not bleeding with positives. So do positive 16.0 newtons minus now here's something to keep in mind. I wrote a negative over here because I was accounting for the direction, okay? But in the sum of the forces equation here, I wrote a minus sign as well. That does not mean I put a negative sign in here because I already accounted for it here. So I'm not going to put in that negative 10. I'm going to just put, oops. Well, here, I could either put in the negative. I could change this to a positive. That actually might be better for you guys. Okay, I'll put in the positive and I'll put the negative 10 here. So here, I was already keeping in mind that it was going to be negative, but over here, I labeled that negative to make sure I knew the direction. So I'm going to go ahead and change that minus sign to a plus sign and keep the whole term I had in there. I think that would make more sense for you guys. So then go ahead and do sine of 30 degrees. So you get the sum of the forces and the y equals a positive. Whoa, whoa, whoa. My finger bumped the button. Positive 10.9 newtons. Okay, now at this point, you need to actually draw another diagram. Okay, what you want to do is draw a diagram that looks like this. There's your free body diagram. You're going to label all the sum of the forces on it. Okay, so we're going to have a sum of the forces in this direction because it says it's positive in the next direction, so this is sigma fx. I'm going to have a sigma technically, okay, I didn't get my myself enough room, so I'm going to make this one shorter. Because fx is less in magnitude compared to fy. And so this one up here is sigma fy. And again, you can do either method you want, but for the parallel method, you see that there's your vector. Okay? And that's just going to be sigma f. And that's what we need to find. Well, we know the two legs now. Okay? This is wrong button. Let's do sigma fx, sigma fy. And so we can use Pythagorean theorem again. We have sigma f will equal the square root of sigma fx squared plus sigma fy squared. Sigma f would then equal square root of a positive 8.83 newtons squared plus a positive 10.9 newtons squared. And that would give you sigma f I'll do it over here. So sigma f would be a positive 14.0 newtons with significant figures, because you need 3 significant figures. And we need it to be in polar form, so now we need to find the angle. The angle basically be the same way we did the angle before. We're going to use tangent of theta equals the sum of the forces in the y direction over the sum of the forces in the x direction. So you're going to get theta equals the inverse tangent of the sum of the forces on the y divided by the sum of the forces in the x. I guess I can do it to the right. I think I should be able to fit that. We have tangent, inverse tangent of a positive 10.9 newtons divided by a positive 8.83 newtons. So you get an angle of 51.0 degrees. Oh, I'm sorry, I just realized I forgot to label the angle earlier. You guys should have been able to catch it from my equation, but I'm saying that this angle here is theta. Okay, that bottom right one. And let's go ahead and north. So I'm going to say at. So we're just putting in the angle for the answer there, 51.0 degrees north of east. Okay, that's one answer we needed, so I'm boxing it. Now we need to find the acceleration. It's going to be just as easy as we did it last time. We just take the sum of the forces divided by the mass. It's already isolated, so we can go ahead and say A equals positive 14.0 newtons divided by 27.0 kilograms. You should have an acceleration of positive 0.519 meters per second squared force causes that acceleration, which means it has to be at the same angle. So you have 51.1 degrees north of east. There's your acceleration. So, kind of a long problem because there's two pieces that are completely unrelated. Well, there we go. There it is. So, we had part A in there, part B here. But you can see there really isn't much difference once you're able to get the diagrams. This is why I zoomed out. I wanted to show you this. Let's change this color to yellow. This diagram right here. Oh wait, it didn't change. There we go. That one right there, and this one right here. Very similar. They're just in opposite directions, but once you've gotten to the point where they're in basically cardinal positions, you're able to use Pythagorean theorem and find the angle, and it's straightforward from there. One thing I just realized I forgot to do when I did part B, technically, I'm going to zoom in so you guys can see. I should have labeled the cardinal positions here. I should have gone north, south, east, and west. Yeah, I did draw for part A, but technically when you're doing a new problem you need to relabel it, so sorry I missed that earlier, but I'm sure you guys understood why I did north of east earlier, so I'm sure you guys followed along with it, but make sure when you're labeling it, it matches. As you can see, I still zoom out, so make sure I look at the problem, see if I'm missing anything like that. So you want to make sure when you're doing problems on a test or for homework that you take a look at the problem when you're done to see did you miss any steps. Sometimes